Okay, let us solve one more problem, and in this problem transmission losses are included. So this question was asked in K2012. It says that the figure shows the two generator system supplying a load of 40 megawatt. So this is two generator system, generator 1, generator 2, and the total load on the system is 40 megawatt. This is bus number 1 and this is bus number 2. The fuel cost of generators G1 and G2 are, these are the fuel cost. So this is incremental fuel cost or operating cost? Operating cost. How? Because it is C1. Maybe anything P, Q, Z, whatever. We have to focus on units. So this is in rupees per megawatt hour. So C operating cost will have unit rupees per hour or million kilocalorie per hour. Is not it? So that million kilocalorie can be converted into rupees per hour. But once we are going to differentiate DC upon DP, that will have unit of rupees per hour into 1 upon megawatt, that is unit of P. So rupees per megawatt hour unit indicates that this cost is incremental fuel cost. This may be having any symbol, any representation, doesn't matter. Sometimes maybe IC1, sometimes maybe C1, so we have to be careful and we can recognize the different costs just observing the units, is not it? Okay. So precaution number 1, we have to focus on the units first, not on the symbols. Okay, so these are incremental fuel cost, independent of the active power generation constants. You should be surprised to see that operating cost is not constant, man, for any unit. That depends on active power generation, is not it? So second guess, you can see that this is constant value. So that may be constant for incremental fuel cost. If you are having linear operating cost characteristic, in that case first derivative will give you constant, but linear will be having P as variable. Is not it? How is it possible that the operating cost is independent of the active power generation? Is it possible? No, right? So now you can observe that these two costs are operating incremental fuel cost, not operating cost, right? Okay, again, and the loss in the line is this, half Pg1 square. So load is connected at bus 2 where generator 2 is connected, but generator 1 is connected at bus 1. In order to supply this load, additional transmission losses will be there. So we can observe that is a function of Pg1 generated by G1. So that is given. Sometimes the loss coefficients may be given, B coefficients. So for two plant system, we know that summation I is equal to 1 to 2, I is equal to 1 to 2, right? M or N, whatever, right? So we will have 4 terms and 4 coefficients, B11, B12, B21, B22, and we know that B12, B21 is same. Yes, so B11 will have P1 square, Pg1 square, B12 will have Pg12 like that. Do you remember? Yes, sir. And Pg2, B22 will have Pg2 square. So as here we can observe that in this expression B22 is 0, B12 and B21 are also 0, B11 is non-zero. But it is directly given, so no need to calculate. Sometimes it may be given indirectly in terms of loss coefficients. There also you are smart enough to formulate your loss formula, right? Because you know that PL is nothing but summation M is equal to 1 to K, N is equal to 1 to K. You know that expression. We have already discussed that, right? But it is directly given. And you can sense it as this loss is mainly depending on Pg1 because Pg1 is far away from this load. And this is just two plant system. Is not it? You are directly feeding the this load from G2 and G1 through this line. So losses will be mainly because of this transmission. But it is directly given, and P loss in per unit is equal to 0.5 times or half whatever Pg1 square per unit values. So how to proceed? What is the objective of this problem? The most economic power generation schedule in megawatt is just very simple problem. Here also the optimal loading has been asked on the two generators. Right. So we know the equation. What is that? Okay. What is that? C. Okay. So directly we will write IC1 L1 will be equal to IC2 L2. Is not it? It is equal to lambda. In general, we know that dCi upon dPgi Li equal to lambda. For I is equal to 1 to up to number of units, right? So we have just 2 units. So I is equal to 1 or 2. And what is this? Incremental fuel cost. But that is directly given. So we may write IC1 L1 is equal to IC2 L2. Is not it? What is Li? Li is nothing but 1 upon 1 minus del PL upon del PGI. Is not it? So for I is equal to 1 or 2, we may evaluate L1 and L2. So L1 will be equal to 1 upon 1 minus del PL upon del PG1 is equal to 1 upon 1 minus, what is PL? PL is function of PG1 in per unit, right? So it will be twice of this, that will be 1 and this is PG1. So directly you will write 1 minus PG1. Isn't it? Let's take it. What about L2? So L2 will be 1 minus del PL upon del PG2. But PL is independent of PG2. So partial derivative will be 0. This PL is not depending on PG2. So partial derivative with respect to PG2 del PL upon del PG2 will give 0. Is not it? So you will write is equal to 1 upon 1 minus 0, that is equal to 1. Now we have evaluated L1. We have evaluated L2. We know IC1 directly given.
Yes, sir.
We know IC2 directly given. So just find out the PG1, values of PG1 and PG2. Okay. So we will write IC1 from here. We will write IC1 is 10,000. 10,000 times L1 is 1 upon 1 minus PG1 is equal to, what is IC2? 12,500 times, what is L2? 1. Is not it? So this is our equation. Solving this, you will have PG1. Tell me the value of PG1. 0.2 kilowatt or megawatt? Per unit. Because here PG1 is function of per unit. So here this is per unit. Is not it? From where you got this PG1? Del PL upon del PG1. And del PL is in per unit. So this will be in per unit. And what is the base value for power? 100 MVA. So first write this as per unit. So actual value can be written as 0.2 per unit value into base value. Base value is 100 MVA. So 100, this is active power. So on 100 MVA base, this will be 100 megawatt. That is coming out to be 20 megawatt. So you know PG1. What is PG2? Total load is 40 megawatt. So PG2 will be 20. So you have ignored losses. Remember that power balance equation when you are considering PGI. I is equal to 1 to number of K units must be equal to PD plus PL. It's not it.
Yes, sir.
You might get one option corresponding to that also. So options are also prepared in very smart way. You will be happy that, oh, okay, I have solved it. C is there. Whatever I am getting, that is there. You will be happy. But you have to be careful, right? So, but we don't know PL. We have expression for PL. And that is function of Pg1 in per unit. We have evaluated Pg1 in per unit. So PL will be, PL in per unit value will be 0.5 into Pg1 per unit, that is 0.2. So 0.2 square per unit. So this is coming out to be how much? Is equal to 0.02 per unit, right? So for power, base MVA is 100. So in megawatt, we may write this into 100, that will be 2, right? 2 megawatt. So loss PL is 2 megawatt. This is 40. And we have two plant systems, so K is 2. So this will be nothing but Pg1 plus Pg2 is equal to 40. PD is 40 plus we have evaluated 2. We know Pg1 we evaluated as 20. So this is 20. So write here 20 directly. All values in actual value, megawatt, right? This is in megawatt. This is in megawatt. This is in megawatt. In either way you can evaluate. Either put all values in per unit or in megawatt, actual values, right? So all are in actual, so Pg2 will be actual. So this implies Pg2 is coming out to be 22 megawatt, right? So depending upon the options, you can choose the appropriate option, right? Any questions in this problem? So is this problem also different than the previous one, except we have considered transmission loss? And for loss, if formula is given directly, it's good. If not given, then you can formulate the equation for P loss, you know, B coefficients, right? And you know this relationship. Without losses, you are having IC1 is equal to IC2 is equal to IC3 and so on, lambda. Just we need to evaluate penalty factors of the corresponding plants. And penalty factors are nothing but Li is 1 upon 1 minus del PL upon del PGI. Clear? Any question?